years, again the idea is that B1 can be expressed in terms of A1, A1 can be expressed in terms of B1 in the framework of new defined operations. Similarly, if we are looking in terms of residuum, A1 arrow A2 is same as B2 arrow B1. And even much more, we can define a partial order relation with the help of this operation. We can define a partial order relation if we are having two factorizations, and let us define a relation like this one, A1 arrow A2. So this becomes a partial order relation. So meaning is to say that by using residuated lattices and the concepts available with residuated lattices, we can find out some, means we can define some new operations and we can develop some new theories. Now the thing is that how to use these theories in the framework of an automaton. So when the people are studying this automaton in multi-valued setting, so they think that okay, only we are transferring all the properties known for automaton to means to the concept of this automata theory available in multi-valued setting. But answer is no here, because what I am going to just describe here, that is given in terms of residuated lattices. So meaning is that the theory of lattices can also be used, their properties can also be used to describe some features for automaton in multi-valued setting. And even this has already been seen by us that if we are discussing automata theory in the framework of lattice ordered monoid, so what will happen that most of the algebraic properties of automata theory depend on the available monoid structure. So if we are going in the framework of this residuated lattice, so this is our residuated lattice valued automaton. Again, all the things are same, Q, sigma, and F. But here the structure of F is something like, this is a map from set of input to L power Q cross Q. This is collection of all the maps from Q cross Q to L. Plus two new things are here, I is from Q to L and F is from Q to L. These are also two maps are included here instead of fixing a single initial state. So anything is initialized final if their values is always greater than the smallest element, and if Q is finite, automaton is finite. This is the extension of this transition map T from sigma to sigma star. And actually the sigma star form a monoid, and this is the way how this can be extended. That is, for empty string the behavior is simple, but with this empty string if we are providing some alphabet, so this will look like the composition of these two forms where R is, this supremum is taken over this particular R. So this is the idea how T is extended from delta to delta star, that is from set to monoid. There is one concept that is called complete. Complete meaning is that if we are starting from any state, so we should at least move at least one state. There should nothing should be absurd type of things. So if we are in any state and we are making an input to the system, we have to go somewhere. Second one is deterministic, meaning is that there should be unique final state plus the path should be unique. So this is the meaning that if we are having these two things greater than 0, then what will happen if we are reaching from P to Q and P to R, then Q and R should be same. Similarly, if initial state is fixed, we call this is crisp valued deterministic automaton. And if we are particularizing it and putting a restriction, so what we can get? We can get a simple deterministic automaton. Simple automaton, what is available in our literature. The next idea is that whenever we are looking, means we are discussing about automaton, there should be concept of language, that is if we are starting from initial to final, how to move, that is defined by this particular map. And this is start from initial state, make some transition and go up to final state. And two automaton are equal, that is they are equivalent in their power if they are accepting the same thing. These are two new L-valued languages. That is, begin with initial and don't use any final thing. Begin with initial and take the transition. And if you are taking the transition and going to final, so the whole this L-valued language can be break up in two parts. One is in terms of initial and second in terms of final. Now let us see how these can be expressed by using the concept of factorization. So by using factorization, so if we are having a factorization, let us take, if we are having an L-valued automaton corresponding to this L-valued automaton, construct a factorized automaton. And this Fs is a factorization of a state set of Q. Now the transition map look like in this way. Initial state map is look like in this way. Final state map look like in this way. And now these are the definition given in terms of factorizations. So this is our factorized automaton, and we can again extend it and we can construct the example. Now coming to this one, if we are having a factorized automaton, so how the transition function will behave on input of two strings, and strings are concatenated, then this structure will look like in this way. Now the same structure, if we want to express in terms of factorizations, so in terms of factorizations, this can be expressed in this particular way, where AI, AJ, so BI, BJ is the second component of the factorization. Now the initial language and final language, they can also be expressed in terms of factorization. This can be expressed here. Now the question is, when we are constructing a language corresponding to factorized automaton, what extra we are gaining? So answer is that if we are corresponding to an automaton, if we are using the theory of residuated lattices and we are constructing a factorized automaton, so by the power they are equivalent, meaning is that they will accept the same language. So again the question comes here, if their role is same, they are accepting the same languages, so why we are working on this factorization theory, and after using factorization theory we are constructing something, even finally we are reaching at the same conclusion that their power in the sense of acceptance of language is same. So this is not only the answer, but answer is this particular result. This one is the minimal in the nature. That is, we have reduced the states and we find the minimal number of states which is to justify the same L-valued language. But this is not true for general lattices, provided that our lattice should be right cancellative. So this is actually the answer whenever we are using this factorization concept and the concept of residuated lattices corresponding to an automaton. One can construct minimal automaton, minimal in the sense that the constructed automaton will accept the same L-valued language, but that will be minimal in number of states. So this is the power of residuated lattice. If we are moving ahead, these are example, and actually I don't have, I think, much time, so this portion I will not cover here. Just some category portion I want to cover. That is, category theory is well known for abstractions of these mathematical structures. So there should be some class of object, there should be some maps, just like whenever we are looking for what is category of set, meaning is that set with functions, category of groups, group with homomorphisms, category of topology, that is topological spaces with continuous maps. So this is the idea of category. So for x dash belongs to set, meaning is that this is the notation of category of set, and if there are two object of this set, homomorphism, we can define homomorphism between residuated lattices, and this residuated morphism is given like this one, FHA x dash. This is the direct image of f of a at x dash. There is no need to think about whether when we are defining this map, what about the algebraic structures of residuated lattices, whether they will preserve? Answer is yes. They will also preserve here. And we can show it. So if we are taking all complete lattices and their homomorphism, which is defined here, that also a category. And if we are taking the reduced structure of an L-valued automaton, here we are changing the input set is fixed here. Only we are working with transition map. So one can also define a homomorphism in the reduced way here. That is because there is no initial and final state type of things. So only in terms of transition, this is a map, just like group homomorphism. They also form a category. So what can happen? So if we are taking an L-valued semi-automaton, or semi-automaton, corresponding to this one, we can construct a residuated lattice. And for such construction, the homomorphisms, this is typical abstraction is here. How to define homomorphism between such constructed residuated lattices? So this type of map are homomorphism, and if they are homomorphism, so such type of complete residuated lattices, they also form a category. The idea is that just like function, there is a concept of functors between two category, and functors between category meaning is that they are preserving the structures, that is objects and morphism in the sense of category theory. So if we are defining a map F from the category of this L-valued automaton to this residuated lattice structure, this category, we can always define a functor, and this functor has two interesting property, that these functors have left adjoint and right adjoint. We are well known that whenever we are talking about adjointness, so in the topology, this is well known that the construction of a stone check compactification is corresponding to topological spaces. Categorically, that can be done by using the concept of left adjoint. So this is the functorial study, or the study of automata and residuated lattices in the framework of category theory. So ma'am, actually means there are number of slides. So should I stop, or I may continue?
Because your time is going to over. You please conclude.
Okay, ma'am. So I will not discuss all the things. The one thing last, and this is, I want to discuss that this is well-known concept in automaton theory that can be extended to L-valued theory of automaton when we are using residuated lattice structure. This is well-known Mahil-Nerod theorem. But whenever we are going for automata theory in multi-valued setting, this Mahil-Nerod theorem holds good, but the condition is that our L star should be locally finite. And locally finite meaning is we have given here that if we are having a residuated lattice, corresponding to lattice, we can construct a semi-ring reduct of L, and this semi-ring, this is locally finite. If its subalgebras are finite, that is too abstract here. For example, two examples are already here. That is, if we are taking with respect of Gödel structure, then semi-ring reduct will always be finite. But if we are going for product structure, that cannot be finite. So these are some of the references I have used. Thank you.
Any question? Any question? Okay, well, I have one question.
Yes, ma'am, please, ma'am.
Throughout the talk, you used residuated lattices. Can we replace this structure by any other algebraic structure?
Ma'am, residuated lattice structure itself is an algebraic structure, ma'am.
Okay, I know. The question is that, can we replace this structure by any other structure?
because the well-known structures are already here, ma'am. For example, whenever we are talking about this Godel structure, Lukasevich structure, actually the thing is we are talking in multi-valued setting. If we are talking in multi-valued setting, there should be at least some lattice structure so that inequality should be there. So this is the
Because
basic idea to create this, to take this one. So by replacing any algebraic structure may not work here.
because this you are taking the residuated lattices. Okay, so in
Ji, ma'am.
place of residuated lattices, can we take any other lattices?
Lattices can be taken, ma'am. Even the people who are working in fuzzy logic, they are working with a replacement of 0 1 with any lattice. So 0 1 can always be replaced by lattice. There is no problem, ma'am.
You use the Gödel algebra and product algebra.
Yeah.
Okay, so is there any relation between these two algebras?
No, ma'am. They are different one.
Okay, so it's well. Uh, yes, the nice presentation you have given, and the talk is very informative. Thank you very much for this nice presentation.
Okay, welcome, ma'am.
I sincerely thank our chairperson of this session, Professor Dr. Asmali, Department of Mathematics, Faculty
Thank
of
you.
Science, Aligarh
Thank
Muslim
you.
University, Uttar Pradesh, and our invited speaker, Dr. S P Tewari, IIT Dhanbad, and all the participants. Thank you once again. And I request you all to join another parallel session going on. Thank you so much.
Thank you. Thank you very much.
Shall I end, ma'am?
Hello?
Hello, ma'am. Shall I end? Do it
Yes,
now?
yes. Okay,
Yeah.
okay.
Thank you
Okay.
so much, ma'am. Thank you.
Welcome.